Hi students. So in this video we'll see how do we find the frequency response of a system. Of course, let us consider a control system having a particular transfer function. So if I want to find what is the frequency response of this system, so when I say, so we know that every system will accept inputs, and that input can be a variable frequency type of input. Suppose if the frequency of this varies from 1 kilohertz to 1 megahertz or 1 gigahertz, so how does this system respond? That is, so on x-axis you will have the frequency. As the frequency varies, so what is the response of the system? Does the response remains constant? Will it vary? Will it increase, decrease? So I want to see the response of this system for different frequencies. Then I'll call it as frequency response of a system. Frequency response of a system. Now let us straight away go to the control system, where in a control system, a system open loop transfer function. Okay, we know that, okay, this is GFS, and if you have a unity feedback, this is how it looks. So this is minus, this is RFS, this is CFS. In this we know that this is having a unity feedback with negative feedback system. So we are going to have open loop transfer function and closed loop transfer function. So this open loop transfer function is given by GFS into HFS, where HFS is the feedback path gain. Since HFS is 1, GFS into HFS for a unity feedback system will be just GFS only. Now once you know GFS, we can actually find what is the closed loop transfer function, which will be nothing but GFS by 1 plus GFS into HFS if it is a negative feedback system, with whatever the feedback is, whatever the feedback is, that is whether the feedback is unity or non-unity, depending on HFS you have. So this will be replaced by HFS. Now if you want to know what is the system response for different frequencies, I have to find the frequency response of this. Now let us take up an example, and when you actually do the frequency response of a system, I should be able to know whether the system is stable or not. So the frequency response talks about how does the response of the system is, and it also talks about whether the system is stable or not. When I say stable, how much stable it is, how much is the increment of gain that is allowed to keep the system in stable condition. All those things I can able to find out using the frequency response of a system. So let us start by taking a typical transfer function GFS into HFS, which is a unity, assume that it's a unity feedback system having this as 10 by S into S plus 10, and this as S plus some 100. So this is my open loop transfer function. I want to know how does the frequency response of this system looks like. Of course you can also consider some 0 also, maybe S plus 50. So I have a pole at the origin, I have an open loop pole at the origin. Suppose if you want to represent the pole 0 representation of this particular system, it has got an open loop pole at 0, it has got one more open loop pole at minus 10, it has got 1 0 at minus 50, and it has got one more pole at minus 100. So these are the pole positions on S plane of a system. Now if I want to plot the frequency response of this, first and foremost thing is that I have to convert this transfer function to time constant form. So we know that a transfer function can be represented in two different forms. So one is pole zero form, other is time constant form. So now this is in pole zero form, because you have s plus 50, s plus 10 and s plus 100. This gives me where is the pole. The pole is at minus 10, the pole is at minus 100, the 0 is at minus 50. Of course there is one more pole at origin. So we know that we can able to find the time response form of the same open loop transfer function by putting this in the form of 1 plus s tau, 1 plus s tau. So meaning whatever you have here 50, you take out 50 outside, then this will become when I take out 50 outside, this will be 1, whereas this will be s by 50. Okay, now you take out 10 here, this will become 1 plus s by 10. So when you take out 100 here, this will become 1 by 1 plus s by 100. So now this transfer function becomes, so it is now 10 into this 50, you take it outside, so then is it not 1 plus s by 50, and then you have s as it is. Let me take out 10 outside, and then so when you take out 10 outside, is it not 1 plus s by 10? I'll take 100 outside, is it not 1 plus s by 100? Now you just put it like this now. So it is now 500 divided by 10 into 100, so that is 0.5. So I have multiplied 10 into 50 divided by 10 into 100, which is 0.5, 500 by 1000, and 1 plus s into what is 50 inverse, it is 0.02, and this is s 1 plus 0.1 s, and it is 1 plus 0.01 s. See now, this was my original transfer function in pole zero form that has been brought to a time constant form of representation of the same transfer function. So it is now 0.5 into 1 plus 0.02s divided by s into 1 plus 0.1s and 1 plus 0.01s. So here also don't think that the pole zero positions have changed. The pole is at, so if you say this is tau p1, if you say this is tau p2, if you say this is tau z, so tau z is at 0.02, whereas tau p1 p2. So what is tau p1? It is 0.1. Tau is actually the time constant, 0.01. So then where is the 0? 0 is actually at 1 over tau z, which is nothing but 50. It is 1 over 0.02 is 50. So where is pole 1? It's 1 over tau p1, which is nothing but 1 over 0.1, which is 10. So where is second pole? It's 1 over tau p2, which is nothing but 1 over 0.01. Is it not 100? So do you still have the poles and zeros at same point of 50, 10, 100 as it was earlier? So pole zero positions will not change, only the representation changes. Next, the question is, how does, this is now GFS into HFS. Now in order to find the frequency response of such a system, I will replace S by J omega. So when I replace S by J omega, so this will become G of J omega, H of J omega. Now you are replacing each and every S in the transfer function by J omega. So then this is equal to 0.5 into 1 plus 0.02 J omega, and this is J omega, and this is 1 plus J 0.01. Okay, this is, let me write this here, and then let me write 1 plus j 0.1 omega. So wherever s is there, I am replacing by j omega. Next the point is, so what is this omega? Omega is a frequency, angular frequency, which ranges from 0 to infinity, because it can be a almost zero frequency, which is DC, to a very large frequency. So now we need to know how does these terms. So what are the terms you have? The terms what you have is 1 over j omega 1 plus 0.02 j omega. You have 1 over 1 plus 0.1 omega. You have, so these are the terms what you have, 1 over 1 plus j 0.01 omega. So we are interested in what is the response of the system if you have the term as 1 over j omega, this and also for 0.5. So since 0.5 doesn't have a omega, the omega doesn't have any impact on this. So if you know how does individual terms affect, or individual terms will be affected by this omega, then we can know what is the overall effect of what is the effect of omega for the overall system. So let us now start understanding what is the frequency response of individual terms. That is, if there is a finite 0, how does the frequency response looks like? If there is a finite, this is a pole, this is a finite 0, and if there is a pole at the origin, or if there is a 0 at the origin, how does the frequency plot looks like? So when we say frequency plot, there are actually two parameters involved in that. So one is magnitude, other one is phase. So we have to look at both magnitude of GH as well as phase of GH. Of course it is GFS into HFS, but I am simply writing it as magnitude of GH and phase angle of GH. So every term will have its contribution to the magnitude as well as phase. So now let us start with understanding what is the frequency response of a finite pole. So when I say finite pole, assume that I have a pole at 0.01. Okay, let us assume that tau p1 is equal to 0.1, meaning that there is a pole at -10. So now shall I write it as 1 over 1 plus j 0.1 omega. So this is actually 1 over 1 plus 0.1. Yes. So this S is now replaced by 1 plus 0.1 j omega. So this is now ultimately written as this. Now, okay, assume that this itself is G into H. It has got only one pole at the origin. So now this is j omega. So does this, suppose if I have it as 1 plus JB, does this has both magnitude as well as the phase? So what is the magnitude of this term? Is it not under root of a square plus b square? For this is the magnitude. What is the phase of it? Is it not tan inverse of b by a? Is this not the magnitude? Is this not the phase of this particular what is that? Complex term. So do you have a complex term similar to that here? So now I have a complex term. Shall I try to find what is the magnitude of this? Magnitude of G into H is nothing but 1 over root of 1 square plus, what is this b? In place of b you have 0.1 omega. Can you see it is 0.1 omega whole square? So as you have a plus jb is written as under root of a square plus b square. In place of a you have 1, in place of b you have 0.1 omega. 0.1 omega is the value of so and so. Now how about magnitude? Since since it is there down here, so since it is 1 over so and so, this will be minus tan inverse of b by a. So typically this is written as tan inverse of b by a, that is imagined by the real. Since it is in the denominator, it is minus of tan inverse of b by a. So what is the phase angle of this? Phase angle is minus tan inverse of b by a. So what is b here? This is 0.1 omega by 1. 0.1 omega by 1. So this is phase of GH. So now, as we know, the magnitude changes, or when frequency changes from 0 to infinity, the magnitude will also change. So we know the extreme values of omega. What are the extreme values of omega? 0 to infinity. So let me write omega here and magnitude. So extreme value is 0 and infinity. So this is the magnitude. Let me put this in dB also. dP is nothing but 20 log of that whatever magnitude you get. So if it is 0, can you see this becomes 0 here? So when omega is 0, can you see it is 1 over 1? Is it not magnitude? So this is 0. Will it not become 1? This is magnitude 1. So when it is magnitude 1, what is 20 log of this magnitude? It's actually 0. Now let us take the value of omega as, maybe let me take it as, let us take a very large value. Here the pole is at, where is the pole? The pole is at minus 10 on your S-plane. So let us take the omega as something like 100, and let us try to find out what is the magnitude. So magnitude is how much? If it is 100, so now what I'll do, 1 divided by under root of 1 plus 0.1 into 100 whole square. Can you see it is now? So it is under root of it is given by, for 100 it is 0.0995. And what is the 20 log of that? Shall I do 20 log of 0.0995? Can you see it is minus 20 dB? For 100 as the value of omega, this is minus 20 dB. Let us do it for 1000. Let me increase the value of omega by 10 times. When I increase it by 10 times, so now shall I put it as 1 divided by under root of 1 plus, because 1 square is 1, plus open the parenthesis 0.1 into how much is, this is 1000. Okay, what I'll do is let me make it as alpha a, so that I can keep substituting. Alpha a close square is calculate for 1000. You see it is 9.99 e power minus 3, that is of course e minus 3. So next let me do it for 10. When I do it for 10, this is now 10. Can you see it is 0.707. I'll do it for 1. Calculate for 1. Is it not 0.995. Let us do 20 log of all this. So what is 20 log of 0.995? Is it not minus 0.043? What is 20 log of 0.707? Can you see, is it not minus 3? So what is 20 log of 9.99 e minus 3? Can you see it is minus 40 dB? These are all the magnitude of this equation for different values of omega. So let me also write the phase. Of it. So phase is what? Minus tan inverse of minus tan inverse of let me pay 0.1 into alpha a. So what I'll do, I'll calculate for 0 because omega is 0. Can you see it is 0 degree? Next, calculate for omega is equal to 1. Can you see it is minus 5.8 degree? Calculate for a is equal to 10. What is this now? When a is equal to, so this is at minus 57 degree. So then calculate at 100. So it is, just a minute, okay, let me put it in, I think this is not in degrees, I think it's let me just find out what is just one. So tan inverse of 0.1 into alpha a, close the parenthesis, calculate 100. One second, let me just do it again. So I just can see I have edited like this. So for omega is equal to 1, it's 5.7. Calculate for omega is equal to 10, it is 45 degree. This is minus 45 degree. Calculate for omega is equal to 100, it's minus 8, because this minus is coming because of this. When it is 10,000, when it is 1000, it is minus 89 degree. So when it is infinite, we know that it is minus 90 degree. So when it is infinite, we know that this is 0. So this will be, of course, it will be minus infinity. It will be minus infinity. So what we are trying to do is we are trying to find out what is the magnitude for different values of omega, the absolute value, and it is, of course, this is in dBs, and this is the phase angle in degrees. Suppose if you summarize this, now let me just write it for different values of omega. What is the magnitude? Can you see when the magnitude is, this is very very small, do you have the magnitude as 1 here? This is 1. So maybe for 1 it is this, maybe you can make it as 0.1. Suppose if it is 0.1, can you see what is that? So 1 divided by square root of 1 plus 0.1 into 1 whole square, close the parenthesis. This, can you see it is 0.995. What is 20 log of this answer? Can you see it is minus 0.0432. Of course, phase angle you can find out. What is phase angle? Tan inverse of 0.1 multiplied by 0.1. Can you see the phase angle is 0.57 degree, which is minus. So what I mean to say is, for lower magnitudes, can you see the magnitude is, of course this magnitude is 1 in terms of ratio, but in terms of dB it is 0 dB. It is 0 dB in terms of dB. In terms of absolute magnitude is 1, but when you are representing this magnitude in dBs, so it is 0. This is for 0 radian per second. For 0.1, is it almost 0 dB? Is this almost 0 dB? For 1 also it is almost 0 dB. Can you see you have something like this? So this is 0 dB line for lower values of omega. Let us take omega is equal to 100. Let us take omega is equal to 100. At omega is equal to 100, what is the magnitude? It is minus 20 dB. So if I take this as minus 20 dB, can you see is it coming here? So for a value of 1000, what is the magnitude? Minus 40 dB. Can you see it's here minus 40 dB? So now if you actually do it for 10,000, this will be minus 60 dB. It will be something like this. Meaning, for lower values of omega, magnitude is 0 dB. For very large values of omega, so this is reducing at a slope of minus 20 dB per decade. Meaning, when the frequency changes by 10 times, can you see, is it going from 100 to 1000? By how many times it has changed? This has changed by 10 times. Can you see from 1000 to 10,000, it's actually into 10. So it's a decade change. So when it increases by 10 times, the magnitude is increasing in negative direction by 20 dB. Correct? This is going down by 20 dB. This is also, can you see, it's again going down by 20 dB. Down, I'm saying it as it's going negative, more negative by 20 dB. So this is a line with minus 20 dB per decade, whereas this is a straight line. Suppose if you extend this line and extend this line also, they meet at a certain point. Suppose if I extend this, because these were the points for larger frequencies, these were the points for lower frequencies. If you extend these two lines asymptotically, they actually meet at 1 radian per second. This is asymptotic extension. I know this, I am extending them asymptotic. I am just simply drawing that, extending that, testing it. So at 1 radian per second, both of them will meet. But in the actual sense, can you see the magnitude is minus 3 dB at 1 radian per second? The actual plot looks like this. So actual plot is certainly coinciding with this plot. The plot here also it is same, but the actual plot slightly deviates here at this point. The deviation is how much? This is the actual value, which is here minus 3 dB. This is the asymptotic value. So asymptotic is an approximate value. So the actual value is minus 3 dB down at what frequency? Sorry, this is not 1, this is actually at 10. Actually we had it at 10. So this is not at 1, this is actually at 10. At 10 radian per second it is minus 3 dB. At 1 it is still almost, at 1 radian per second it is still almost 0 dB. So at 10 radian per second I have a magnitude of minus 3 dB. In the actual sense, in the asymptotic way, we can treat that this the asymptotic magnitude plot of a system having a pole at 10 radian per second look like this. So this is a straight line. Okay, this is the representation of 1 over 1 plus 0.1. Yes, such a pole which is at minus 10 will be represented in the frequency response as a line with 0 dB magnitude with no slope. It will be there like this till 10 radian per second. Afterwards it goes down with a slope of minus 20 dB per decade. 20 dB per decade. So this is omega, this is magnitude. On the same lines, suppose if I want to know what is the plot of 1 over 1 plus 0.02 s. So what I have to do? I have to replace s by j omega. Will it not become 1 plus j 0.02 omega? So what is 0.02 1 over? That is, what is 1 over of this tau? Tau is actually 0.02. So 0.02 inverse is 50. Can you see this is my omega f, I'll call it as. So now what is the representation of this? The representation of this is, so you can identify a cutoff frequency 50 here, and this magnitude is of 0 dB till 50. After 50 it goes with a slope of minus 20 dB per decade. This is the asymptotic plot. Because in this frequency response we plot only the asymptotic plot represented by a zero slope line at magnitude of 0 dB till the cutoff frequency, which is 50 in this case, and after 50 it goes with a slope of minus 20 dB per decade. Suppose if you have a 0 at a finite point. Okay, this can be done for any number of, supposing that you have 1 over 1 plus 0.25. yes. So can you see here the slope is 0. There's a change in slope. Where does the change of slope happens at 1 over tau p, and that slope is negative slope. And here is also what is this 10 was actually 1 over 0.1. how this you got it as 50? It is 1 over 0.02. Suppose if you have it as 0.25, then what is tau p? Is it not 0.25? Then what is the pole position? Is it not at 1 over 0.25, which is nothing but 4? So meaning for this it will be a 0 dB line till where? Till 4 radian per second. Afterwards it goes with a slope of minus 20 dB per decade. On the same lines, if you have a 0 at any point, so it's very simple, which you can prove the way how we have done it here for a pole. If you do it here for a 0, assume that you have a 0 something like this 0.1, yes, because this is numerator. So if this is your GFS into HFS, assume that you want to represent only a 0, so then it will be, because what is tau z? This is 0.1. What is z pole frequency or z frequency? It is 1 over tau, which is 1 over 0.1, which will be 10. So now till 10 radian per second, this will be a 0 dB line with no slope. So after 10 radian per second, in the previous case, if it was a pole, this was reducing with a slope of minus 20 per decade. Since it's a 0, it increases with a slope of plus 20 dB per decade. So it's an increment of slope after cutoff frequency. Suppose if you have something like this, 1 plus 0.05 s, this is my 0. So how does it look like? So up to what frequency this will be of constant magnet, 0 dB. So this will be 0 dB up to 1 over 0.05, which is nothing but 20. So 0.05 is 20. So till 20 radian per second, this will be having a magnitude of 0 dB. Afterwards it increases with a slope of plus 20 dB per decade. So of course, which can be certainly proved the way how we have done it here. So then what you have to do is you have to simply make out this, instead of this negative 1 over this here, you simply make it as 1 over root, not 1 over, just root of 1 square plus 0.1 omega square. Suppose you are looking for 1 plus j.1. So this is how the magnitude will vary for a finite pole. You can similarly have a look at the phases. So let me just write the phase here. So let me just put the phase plot on the right hand side. So let me take this as 0 degree and this as minus 90 degree. See now, this is omega 0. If omega is 0, what is the phase? Can you see the phase is almost 0 degree? So as the value of omega increases from 0 to infinity, can you see the phase is going from 0 to minus 90 degree? So it actually goes like this. If this 0 degree and this will coincide, it actually goes like this. So when omega is 10, the phase is minus 45 degree. That is, when omega is 10, this phase will be minus 45 degree. So you can just think of, this is, if you say this is 5, this is omega, this is 0 to infinity. If this is 0 degree, if this is minus 90 degree, it actually goes like this. So initially phase is 0 degree, then it becomes reducing, and then finally it becomes minus 90. So this is minus 45 degree at a frequency corresponding to 1 over 1000. So for this case, when omega is 10 radian per second, we had a phase of minus 45 degree. Can you see? We had a phase of minus 45 degree when the omega is 10 radian per second. So phase changes with respect to omega, magnitude also changes with respect to omega. Phase is an absolute value that I am putting, whereas the magnitude I am making an asymptotic one. So we will not be plotting a curved path for the magnitude. Instead we will plot a straight line, that is till cutoff frequency it is 0 dB line with magnitude 0, and then afterwards it goes with a slope of minus 20 dB per decade, because you have a finite pole. In the next video we will see how do we plot it for a pole at the origin or a 0 at the origin. So with that, after that we'll just move on to actually how do we find the frequency response of a complete system having a number of poles and zeros. Thank you.